Valparaiso University, a former co-organizer of this seminar. I will speak about pattern avoidance in trees. We're going to take Lara out for dinner at the Evelyn restaurant in New Brunswick, and everybody is welcome to join us, but please let me know immediately after the talk.
Thank you. Well, it's very good to be back here. It's been a while, but the main thing I want to point out on this title slide is not my title or my name, but this line right here. These slides are already on my website, so if you see a picture or an equation you want to know more about, and you say, oh wait, I didn't get that down quick enough, just get this and you have access to it. All right, so we're talking about trees, and you see the things I'll talk about in the order I'll talk about them on the left, but I think it's actually more useful to give you a picture outline. So this is really what we're talking about today. I have two different kinds of tree patterns I'd like to address, and the main one, the theme throughout the talk, is these non-contiguous trees. But a lot of what I want to say about them is comparing and contrasting them with these contiguous trees. So the beginning of the talk will focus on these two circles. And part of why I like the non-contiguous trees so much is because you can translate a lot of the results with non-contiguous trees to results about permutation patterns. So at the end of the talk, we'll focus more on how these two circles intersect.
They're the ones that lose their leaves in the winter?
Could be. We'll find out in a couple slides. But for the beginning here, we're going to focus on trees. So before I even get to what these two kinds of tree patterns are, let me tell you a little bit why you might care about trees. Some early references about tree patterns in the literature have very concrete computer science motivations. So for example, let's see, this is 23 years ago now, Flageolet and co-authors were looking at compactly storing things in computer memory that have lots of repetition in them. For example, we've all made it past calculus 1, so you know to take the derivative of this expression, you need the chain rule, the product rule, the chain rule a couple more times, and it's going to explode into a mess, right? Well, here's a tree picture of the derivative of that expression. I get the expression represented by this tree times the expression represented by this tree. And you notice there's a lot of copies of similar small trees inside of here. For example, e to the power x plus 1 shows up 1, 2, 3, 4, 5 times. And if I have a tree like this where there's lots of repetition of smaller subtrees, and I know about that, I could encode the smaller subtree once and have pointers to it. So recognizing copies of a tree within a larger tree has some very concrete computer applications. Much more recently, if you follow the archive, labeled trees have showed up for other reasons. The non-associative algebra people care about them. They use the trees to represent different amounts of associativity, and then recognizing smaller trees inside of larger trees tells them more about algebra. So trees have been around for a while with applications outside of, hey, let's count. But also in the last 4 or 5 years, if I take the labels off the trees, I get some nice problems for computer experimentation that, as I've already hinted at, can tell me more about permutation patterns, and that's the thread I want to focus on today. So let me tell you a little bit more about this branch of research with the unlabeled trees. And here's the history as far as I know it. In 2009, Eric Rowland defended his PhD thesis, probably in this room, and one of the chapters was about contiguous pattern avoidance in binary trees. And I'll tell you some more highlights from Eric's results in a couple slides. But after I heard Eric give a couple very nice talks on these contiguous patterns and asked him some questions and was sure he was tired of working on them and moving on to other things, I used Eric's work as kind of a spinning off point for 3 different summers of projects with undergraduate researchers at my home institution. So my first group just took Eric's results and instead of binary trees said, what about ternary trees, 4-ary trees, and so on, to see what sequences we get. And then the 2011 and 2012 groups made a more general definition of tree pattern and saw what came from that. The first group focused on pattern avoidance, the second group focused on pattern containment, and you're going to see results from both of these groups in the talk today. So, now that I've given you a lot of history but not a lot of precise definitions, let's get some definitions so I can do some math. Here are the trees that we're talking about today. They're rooted, ordered, and full binary. So rooted just means I have a root vertex, and there are a couple different conventions. My roots will always be at the top, so my trees grow down rather than up. The trees are ordered, so I can tell my left apart from my right. If I took the reflection of this tree, that doesn't count as the same tree. And they're full binary, so every vertex either has 2 children or 0 children. There we go. So these are the trees I care about. And T sub n is the set of n-leaf binary trees, so let's see, this must be a member of T7. And now that you know what trees I'm looking at, here's my big question. How many trees with n leaves avoid a given pattern? Now I still need to tell you what pattern means, right? So let's start with Eric's definition, since it's the original one in this sort of research. This is what contiguous tree pattern means. Big T contains little t, if and only if it has little t as a contiguous, rooted, ordered subtree. So hopefully more clear with some examples. I have a 5-leaf tree over here. And we see it contains this 4-leaf tree. If I just cover up this much, there's the 4-leaf tree. We see it contains this one, because if I cover up this much, well, there's that 4-leaf tree. But it avoids the tree on the far right, because you don't see any vertex that has both grandchildren and great-grandchildren all leading to the left. So this definition is basically cut the tree out of the screen and be able to paste it over part of your tree. Well, now my big question was how many trees avoid a given pattern. So let's just start with some small examples, make sure we're all still awake at 5 in the afternoon and see how it goes. How many 1-leaf trees are there? 1, right? So there it is, it looks like that. Nice and simple. And the number of n-leaf trees that avoid that is 0. Every tree has a root, so there we go. Number of 2-leaf trees, just 1. It's right here. And the only tree that avoids that is the one up here. Right? Everything else, if the root has children, you have this sitting at the top of your tree. The 3-leaf trees are these 2 right here. Now what does a tree have to look like to avoid this? I can't have a vertex that has grandchildren to the left, so every time I make a new generation, it has to lean to the right. Only right-leaning trees avoid this. Therefore, there's 1 n-leaf tree. And if I just take the reflection of the argument I just made, there's 1 n-leaf tree that avoids this.
What does that 1-leaf tree look like, the one that avoids that?
The 1-leaf tree is this one right here.
Oh, yeah. Oh, I see. Yeah. Right.
Okay?
Good.
So I think it's always good to start with these cases, because sometimes pathological things can happen, but is everything clear with these cases so far? And I'm not going to make us sit here and count through things all day, but I think it's also good to look at the 4-leaf trees. So, how many 4-leaf trees are there? Catalan, so what's the next Catalan number?
5.
5. So let's see if I can draw them all. We should have the one that always leans to the left, like so. We should have a kind of crooked one that leans to the left and then leans to the right. We should have a very symmetric one that looks like this. Yes, and then mirror images. This one I don't need to draw the mirror image because it's already there, but I get this one and this one, and by the argument we just had with the 3-leaf trees, I know I should get the same sequence from either one of these 2, and I should get the same sequence from either one of these 2, so I really just have 3 cases to consider. So I'll do them in what I think is increasing order of difficulty, and we're going to go from right to left across this list. So this tree, what does it mean to avoid this tree? It means I can't have a vertex that has grandchildren both to the left and to the right. So at every generation, I have an either-or decision. Do I give 2 more vertices to the left or to the right? Well, powers of 2. Okay, so that one, so far so good. I still see people looking happy. We get powers of 2 from avoiding this tree. 1 case down, 2 more to go. If I look at this slightly crooked one, a typical tree avoiding this doesn't look at all like the previous slide, but it still has some nice structure. As soon as I give a vertex extra descendants to the left, I can't go to the right, I have to keep going to the left. So you can really build this tree by making a bunch of either-or decisions as well. You start here and say, okay, well I'll go to the left, and I'll go to the left, and I'll go to the left, and as soon as you say go to the right, that means start building another thing over here. Okay, so again, we have powers of 2 going on here, even though the trees look very, very different. Now the last tree I need to look at is the first one I wrote down over there. And it's this one that leans to the left. And I don't just have one typical tree that avoids this, but here are several examples. What you can look for is at the root, if the left side of the root doesn't have any more vertices than just this one, I just need to fill in an n-1 leaf tree avoiding t over on the right. And if the vertex to the left of the root does have more children, I can't put anything here. I just need to fill in subtrees avoiding t here and here. And I won't go through details, but from that description I just gave, you can see that the number of trees avoiding this follows the recurrence for the Motzkin numbers, and this was shown by Donahue and Shapiro. So we get another nice sequence here, even though it's
the
not.
notion of avoiding is implicit? Avoiding trees is implicit in the work?
Yes,
But they don't mention it explicitly.
correct.
No, they do mention it explicitly. It's a slightly different.
So it's a good.
It's there. It's there.
But the notion came from you.
The notion came from me, but in this particular case, it's in that paper.
Oh, yeah. But they didn't consider the
No, they didn't consider the general
No.
situation.
Just the case that gives Motzkin numbers.
Yeah, and did they use the word avoiding?
I think so.
Okay. Okay, by avoiding a specific thing.
Right.
Right, just this one specific one. So, to summarize what we've just seen, here is the data for avoiding one contiguous tree pattern with up to 4 leaves. We get one sequence for avoiding a 1-leaf tree. There's one possible sequence for avoiding a 2-leaf tree or a 3-leaf tree. But with the 4-leaf trees, we get one of these 2 sequences. And Eric kept going from here. I won't make you sit through all the details. I'll just tell you a punchline. Eric was able to develop an algorithm that would give you a functional equation for the ordinary generating function for the number of n-leaf trees avoiding a tree pattern. As a consequence of his algorithm, these generating functions are always algebraic. And he did quite a bit more, but I just want to talk about avoidance for the moment. He has this OEIS sequence, which has exactly 8 terms in it. The next term is unknown. But we saw up to this point, we got one sequence for avoiding a 1, 2, or 3-leaf tree, 2 sequences from avoiding 4-leaf trees, and then Eric was able to completely classify which trees give which sequences up to 8-leaf tree patterns. So that's the background I'd like you to know about contiguous trees before I tell you the new definition for pattern avoidance that's kind of the feature of the rest of the talk. So here's our new definition of tree pattern. And this was motivated actually by thinking about permutation patterns, because that's my default thing to think about. So a non-contiguous tree pattern is a little bit different because big T contains little t, if and only if you can contract edges by pairs and find your smaller tree inside of it. So when I say by pairs, I mean that if I chose to contract, for example, this edge, I have to contract the other edge that grows down from the same parent vertex. Okay, so if I contracted this, I would also have to contract this. If I contracted this, I would also have to contract this, and so on. So anything that this contained in the old sense is still inside of here. This is still here because I can contract these 2. This one is still sitting right here because I can contract the 2 edges at the top. But before, this tree avoided the one on the far right, and now it contains it because if I contracted these 2 edges, I would have that tree right there. Okay, so that's the new definition, and I won't make you sit through all the individual cases again, but I'll give you a summary, and you can tell me what's different compared to the contiguous tree patterns.
No, that's good.
Sorry, real fast. That makes some contractions illegal, right?
Correct.
Okay.
Yes. So you want a sequence that still has well-defined, nice, rooted, ordered, full binary trees.
So it seems easier to count than the previous.
It seems easier to count because, like Neil said, there's no Motzkin anymore. And in fact, if you're feeling really bold, this slide might make you make a conjecture. Is anyone feeling particularly bold, or is that my job?
It's rational.
About 3 to the n minus 3 is the next one.
3 to the n minus 3 is the next one. And by the next one, you mean?
I don't know.
Well, the main difference that Neil pointed out was we had 2 different sequences we could get for 4-leaf trees here. with contiguous patterns. And now we got the same sequence for all of these. So my really bold conjecture might be not only do the sequences seem to be nicer, not only did Motzkin go away, but maybe the sequence I get only depends on the number of leaves now. Now this isn't really enough cases to substantiate that, but if you're feeling bold and working with undergraduates, it's a reasonable conjecture to play with for a little bit, right? And it turns out to be the case. So here's our definition. Notice instead of A, like I was using for contiguous trees, I'll use AB now when I'm talking about avoiding non-contiguous trees. And I'll let G sub t be the generating function for the ordinary generating function for the sequence you get from avoiding tree T non-contiguously. And it turns out, pick your favorite positive integer, pick true trees with that number of leaves, you're going to get the same generating function. So I'm going to convince you why this is true. And here's a little bit more notation to help us out. When we have a tree T, I want to be able to talk about the subtree to the left of the root versus the subtree to the right of the root. So that's what TL and TR are. This picture is about to go away, but this is still here to help you. So with that notation, we have this generating function equation right here. Because if you talk about trees avoiding T, you're going to have one of three cases. You have the tree that looks like this. Well, that's what the X accounts for, because this has one leaf. You have trees where the root has children, and the thing over here avoids TL, but the thing over here just avoids T. Right? This guarantees I can't have a copy of T anywhere. I can't have it here because, well, that's what that says. I can't have it here because if it doesn't even have TL, I can't have T. And I can't have a copy of T including the root because I don't have the right structure over here. And then the other picture is where the left-hand side avoids T and the right-hand side avoids TR. But of course I've just double counted things that avoid TL on the left and things that avoid TR on the right, hence the term that's subtracted. And just straightforward algebra, I can solve this, and I have a recursive equation for computing G sub t, which means what Rowland just said is exactly right. I'm always going to get rational generating functions now, because all the sequences you saw so far had rational generating functions, and this tells me that I'm always going to have a rational combination of rational generating functions. So there's a recursive way to compute this, but that doesn't convince you you always get the same answer yet, so we still need to address that. So before I tell you the theorem in all its full glory, I'm going to focus on a special kind of tree and what this equation does to it. So the name I have for this tree I think actually came from Eric. This is the left comb, because it looks kind of like a comb. It's the tree that always leans to the left. So you see the first few left combs sitting up here. And if I deal with the left comb, that recurrence from the previous slide is quite a bit nicer. Because if I look at the k-leaf left comb, what's the left subtree? It's a left comb with one less leaf. And the right subtree is just this one-leaf tree. So once we get past avoiding this guy, here's what happens to our recurrence. The left subtree is this, the right subtree is that. And it's impossible to avoid this, so this is 0, stuff gets wiped out, and we have a much simpler recurrence. Okay, so that's our generating function for dealing with combs.
So you have some kind of continuous fraction.
Yes.
Isn't it?
Yes. And this I like even better because it just has one recursive term in it instead of two different kinds multiplied and so on. Things just get a lot nicer when you deal with this comb. So now let's go back to the big picture. Remember, I want to convince you that any two trees you pick, whether they're the left comb or not, if they have the same number of leaves, they get the same generating function. And it's a proof by induction. We already saw that this is true if your tree pattern has 1, 2, 3, or 4 leaves. So now we're going to assume that this works if you have fewer than k leaves. Since this is smaller than k leaves, we can just use the generating function for the comb with the much simpler recurrence from the previous slide. And then I look at a tree with j leaves to the left of the root versus a tree with j minus 1 leaves to the left of the root, but both with the same total number of leaves. And using the recurrence from the previous slide, you do several lines of algebra, and it falls out. So, proof by induction, this bold conjecture made by my undergrads is actually true. And now that you've seen that no matter which two trees we look at, you get the same generating function, you might want to look at the generating functions a little closer. So that's what's right here. And for Neil, we have all the EIS numbers. So we've seen up to this point so far today, you have the all zero sequence, the almost all zero sequence, and the all one sequence for avoiding trees with 1, 2, or 3 leaves. Here's the generating function for powers of 2, and so on. And these all are in OEIS for very good reasons. We'll get more to that in the last section of the talk. But I'd like you guys to focus on the coefficients here for a second. And so that other things are a little less distracting, the next slide is just going to have these generating functions. And I know the answer, so just to make sure you guys are still happy with me, what can you observe about the coefficients in these generating functions?
Binomial coefficient.
Okay, that is the fastest anybody's ever said that, but I shouldn't be surprised considering the source. Okay, so there are binomial coefficients going around here. Pascal's triangle is left justified right here. And I've color-coded it so that you can see. From that recurrence with the avoiding the left combs, it shouldn't be a surprise that the numerator of one of these is just x times the denominator of the previous one. And so the denominator here is going to have the same coefficients as the numerator here. Turns out, yes, they're coming from diagonals of Pascal's triangle. So I've color-coded, you see, for example, the 1 and 2 here match up with the 1 and 2 right here. And so on. Are the colors clear? Excellent. So, another induction proof, I can tell you not just am I always going to get the same generating function no matter which 2 k-leaf trees I avoid, I can give you an explicit formula. And it looks like this. You have alternating sums where the coefficients come from diagonals of Pascal's triangle. So this is pretty great because with contiguous trees, we had to stop after a point. We had a technique that in theory works, but eventually you run out of computational power to keep going in a reasonable amount of time. But for non-contiguous tree patterns, I know I'll always get one sequence, and I can give you the generating function no matter how many leaves you have. So that's the story so far with avoidance with contiguous trees versus non-contiguous trees. The contiguous ones came first and had nice results. The non-contiguous ones came later and have an even nicer overall characterization. So let's go back to our Venn diagram. Do you notice what's different now compared to the first one I showed you, or?
Colors changed.
The color changed, but you knew that already.
No, I didn't.
Okay. We're still going to talk about trees, but in my mind at least, orange is the opposite of blue. Instead of avoidance, I want to take a moment and talk about containment. So, we're still in this part, but we're talking about a different question. And we'll start with contiguous trees again, see a nice result, and then see what happens when you go to non-contiguous trees. And the result I want to say about contiguous trees is this. It's from Flageolet and Steyert from, 30 years ago at this point. And they say the number of copies of a k-leaf tree in the set of all n-leaf trees doesn't depend on which k-leaf tree you picked. And the number of copies you get is exactly this binomial coefficient. So if I picked any one of the 4-leaf trees over there and looked at how many times they were contained in the set of all 5-leaf trees, I should see each one of those exactly 6 times. And to illustrate, here are the 14 5-leaf trees copied twice over. Up here I've listed the number of copies of that tree at the top in each of them. So there's 2 copies of it here, 1 here, 1 here, and so on. Down here I've listed all the 5-leaf trees, but with the number of copies of that symmetric 4-leaf tree. And again, the distribution is totally different, but the total number of copies is the same and agrees with the result on the previous slide. Any conjectures what happens when I switch to non-contiguous avoidance besides the numbers get bigger?
Stops being the same.
Stops being the same?
Well, it was the opposite of that.
Yeah, well that's one of the 2 conjectures, and so that's a reasonable guess. So let's find out. I'm going to do number of copies of these same 2 trees in all the 5-leaf trees, but non-contiguously. Again, the numbers should go up because the definition of non-contiguous included the definition of contiguous. At least for these 2 trees, they're the same. So again, you notice the numbers went up, but the totals, at least for these 2 trees, are the same. This is the kind of question I'm looking at. How many copies of a particular tree are in the set of all larger trees with a given number of leaves? The theorem from my 2012 group is this. Again, it doesn't depend on the tree, which surprised us a little bit, but is a very nice parallel to the flageolet and Steyert result. And we have this nice bivariate generating function where x keeps track of the number of leaves in the larger set of trees, and k is the number of leaves in your tree pattern. And so I've expanded this just enough that we can find the 10 from the previous slide. The number of times a 4-leaf tree is contained in the set of all 5-leaf trees is 10. Okay, so it turns out that we have this nice, it's always the same result when you switch to non-contiguous trees for containment as well. And that's the story I want to tell about trees for the moment. They'll come back. But now we're ready to start bringing in the permutations. My main area of research as a graduate student was with pattern avoiding permutations, which have all kinds of applications, especially with characterizing which things are sortable in different abstract data structures, but in all kinds of other things. There's a very large community that just worries about avoidance and permutations. So once my undergraduates had all these tree results, I was curious if there was any relationship with permutation results. So for a moment it'll feel like a totally new talk while we get some permutation definitions, but it's just so I can build up the other side and tie things together. So I'm going to use script S sub n for the set of all permutations of length n. I believe you all know what a permutation is, but these are here to emphasize I write permutations in one-line notation. So in my mind, a permutation is just a list of the numbers 1 to n in some order. And I need a way to look for smaller permutations inside of larger permutations, so this definition is a step in that direction. If I have a list of numbers, the reduction is what I get by replacing the ith smallest number with I. So for example, here the smallest number is 1. The next smallest number is the 3, so I put a 2 there. The next smallest number is that, so I put a 3 there. The next smallest number is that, so I put a 4 there. There's nothing to stop you from doing reduction where you have repeated digits, and there's nothing to stop you from having the reduction of a string be the original string. Now before I tell you what a permutation pattern is, I want to give you a visual way to think about permutations as well, because it's going to be very handy coming up. So when I have one of these permutations, this is how I'm really thinking about it. I graph the point I comma pi of I for every digit in the permutation. I have a nice permutation of like 7 here. For example, the first digit is 7. I plot 1 comma 7, and so on. Okay, so when I talk about permutations, often I don't actually write it in one-line notation. I draw you a picture. And now we're ready for the definition of permutation pattern. So pi contains rho if I can find k indices so that when I look at the digits of pi in those positions, and I take the reduction from 2 slides ago, I get rho. So lots of examples here with the permutation from the previous slide. You can watch the digits up here to see them change color, or you can watch down here. This permutation of length 7, for example, contains 1, 3, 2, because if I look at the digits 2, 4, 3, they're in the same relative order as 1, 3, 2. The reduction of this is 1, 3, 2. Or equivalently, I can look at the 2, 4, and 3 plotted here, and I see that that graph looks just like 1, 3, 2. That's not the only copy of 1, 3, 2. If I look at 2, 5, 3 or 2, 6, 3, they make that same shape. So this permutation of length 7 contains 1, 3, 2 3 different times. Similarly, I see 4, 3, 2, 1 in here in 3 different ways. Okay, so these are patterns contained in this permutation of length 7, but it avoids 5, 4, 3, 2, 1 because there is no decreasing subsequence of length 5. Is this definition clear? Because the permutations are going to get messier shortly. Okay. So my notation for pattern avoiding permutations is up here. Script S sub n was the set of all permutations. If you see a parentheses with rho, I'm talking about permutations that avoid rho. And if you see lowercase s sub n, that's just the cardinality of that set. And what I really care about is permutations that avoid 1, 3, 2. And this is the graph of a typical permutation that avoids 1, 3, 2. The largest digit has to be somewhere, so let's say it's in position I. And then if you avoid 1, 3, 2, all the other points in your permutation have to be in one of these 2 boxes. Because if I had something smaller here and something larger here, I just made a 1, 3, 2. Everything on this side has to be larger. Well, that means the number of 1, 3, 2 avoiders satisfies this recurrence. And with the right base cases, that's a recurrence that we all know and love for the Catalan numbers. Now we've already